Hello everyone, my name is Avkash, and in this tutorial we are going to go little more deeper to understand how does the model explainability works with LIME, which stands for local, interpretable, model agnostic explanations, or LIME. Whenever we are using the LIME for explaining our model results, we always used a surrogate model or a new model to explain the predictions made by the given model for source data. So with the LIME explanations, you need two things. First, you need your model, which is used for prediction, and you also need the inference data, which was used to generate the predictions so that you can learn what was predicted and why it was predicted. Sometimes predictions are correct, but the reasons for the predictions could be wrong. There are several important reasons you need a model to predict. However, the most important reason at the top is that a model is predicting a positive results for the wrong reasons, and that is the very big problem if it is happening in your model. So using a surrogate model, you can understand if the model prediction was as such, what were the prominent reasons were used to predict such results. So with LIME, a surrogate model is created based on a certain type of regressor to generate the predictions based on the local proximity of the model predictions. And the reason we are using a local or a surrogate model to explain the predictions which are local to the given prediction, because it is simpler to explain the result locally rather than explaining them globally. So the LIME model explanations can be used with any tabular data, whether it has the binary or the multi-class classification problem. If you are using regression or the tree-based algorithm to solving various classifications or the regression problem, you can definitely use LIME to explain your results. If your data is unstructured, such as images, large documents, even audio files, you can use LIME explanations with them as well. Most of the popular machine learning libraries or engines such as H2O.ai, Scikit-learn, XGBoost, LightGPM, Keras, PyTorch, and many others, the models generated by these frameworks can also be used with LIME to generate the predictions explanations. Technically, any model can be used. However, the LIME methods are best fit for the supervised models in general. Before we go further, by deep diving into the explanations made by LIME, I just wanted to make one thing clear, is that the LIME explanations are different than feature importance. Because when we are using the linear machine algorithms to fit a model, the most of the time or almost every time, the predictions are the weighted sum of input values. In some cases, when you are using the logistics or other algorithms, such as tree algorithms, coefficients plus the various regularization method can also be used with the coefficients. So all of these algorithms, they find a set of coefficient to use as a weighted sum in order to make the predictions. And these coefficients are actually used as the feature importance score. However, when we use LIME-based prediction, we do not use these coefficients. However, we generate a new model which is local to the given prediction. And if you are using unstructured data such as images and other audio files or large documents, in that case you may not have the feature to start with. However, those features are generated when the machine learning in progress. So that way you can make sure that the feature importance is very different than the explanations made by the line explainable model or line explainability model itself. And if a model is predicting this image as an elephant, the line model is going to explain the within the given image what were the certain areas which are responsible to predict this image as an elephant. So here you could see that how an elephant was predicted as an elephant through a series of step-by-step processes to generate the explanation for the result, and what particular image sections were highly responsible for predicting a given image belongs to a certain class. In this second explanation of line, we could see that how the superpixel boundaries are created, and then the dark black color is being filled to those certain areas which are responsible for explaining this image belongs to a certain class. And finally, the line explanation image shows that the certain area of this image has been used to predict this image belong to a certain class, such as elephant in this given example. Here in this inference result, you could see that model has predicted a certain value to be poisonous, and the main reasons which were responsible for these results to be poisonous are given in this orange color features along with their weight to generate the such prediction. So in this tutorial, we are using two separate line implementations to learn how line works and how we can use line to generate the model prediction results explanations. So in this tutorial, we are going to learn how the model explainability works with line. We are going to use three different models: EffecientNet, ResNet, as well as the Inception, and learn the line-based model explanations in two different ways. In this first Jupyter notebook, we are going to learn the predictions made by the Inception model for given source image as African elephant. What were the reasons? And those explanations we are going to see, such as using the superpixel boundaries, and what were the primary areas and the reasons why this image was explained as African elephant. The second Jupyter notebook, we are going to see the new implementation of the line model explainability project, a different explanation as explained in this GitHub repo. So this is a different implementation of the same line research paper, and this Jupyter notebook has two separate objectives. One, to show that line is model agnostic by using the ResNet and the EffecientNet model, these two, and explaining the same source image as the elephant, and the explanations are showing as this: first showing the superpixel boundary, then generating the perturbed image, and finally showing the certain area of the given image which were used for predicting this image as the African elephant. So the reasons were responsible to make this source image predict as the African elephant. These explanations are made using the model which is the EffecientNet model and by source image, and the later we are using these explanations which are for the ResNet model and the source image. So in this tutorial, you are going to learn the model explainability through line with two different examples. So let's get ourselves started. Here in this example, we are going to learn the line-based model explainability through an example which is created by the line team itself. First, we are importing few of the Python modules such as Keras, InceptionNet, because we are using the pre-created or pre-built Inception image classification model. We are also importing skimage.io as well as the matplotlib to generate the plots and NumPy. Once these modules are loaded, first we are downloading the Inception model. So Inception model, which is available at the Google Store, we have downloaded. So now the Inception model is available through this INET model object. So wherever we would want to reference Inception model, we could refer this INET model object. Next step is to load the image from local file system and adjust it in a way so that it can be fit for Inception model prediction. It means when you are going to load the image from the local file system, first you need to read it in a way that it's fit for Inception model input size, which is 299 by 299. Once the image is loaded, that has to be transformed into a format which is read by Inception model correctly. So first we are defining this function, and next here in my local file system content folder, here at my local file system where this code is running, actually this code is running at the Google Colab. So the Google Colab file system, I already have this elephant.jpg image is available. So this JPEG image is loaded from this location, images. So this image, and after that image is loaded, we are running the prediction using this INET model object, which is Inception model, and the predictions, the top 5 predictions for this image are rendered. First one, the African element, has the 82% probability. However, the remaining 4 are Indian elephant, tusker, rain barrel, and the sock has very little, means under 1% the probability. At this point, the model used by us, Inception model, has predicted that this given image is an African elephant. Now we are going to use the line model library to understand what are the reasons where this model, Inception model, is predicting this image African elephant. So very first thing, if you do not have Lime installed in your machine, please install it. Let me run. I think this machine doesn't have Lime, so Lime is installed. After that, we are going to import this Lime image function, which is needed in order to render the results from Lime. So this Lime image explainer function is used as the Lime image explainer because our objective here in this project is the using Lime for explaining the results related with image. So that's the reason we are using Lime image and the Lime image explainer function, which results this explainer object. Now we have explainer object available, and in this explainer object we are making this call to explain instance function where we need to pass the image, okay, which is as type double, and the INET model, the model which we have used, and this prediction method on it, and using the top 5 labels, and rest is just a hide color and the number of samples 1000. It means when we are going to run this code, it is going to generate a local model with a specific to the prediction related to this given image segment, so which is an elephant, and predicted as 82% probability of being the African element. So we are going to run this code. It will take some time to complete, and this process is where the local model is being created in order to explain why this prediction is referred as 82% probability for being the African elephant. So it took about 5 minutes and 58 seconds, almost 6 seconds, to build a new surrogate model which is going to be used to explain the results. So this is the explanation model. So we are going to learn the explanations, and as you could see here, these are the image explanations. So now whenever we would want to explain the results, we can use this explanation object. So we are importing the mark boundaries method from the skimage segmentation, because so that we could show the outline boundaries for specific areas in the given image. So first we are going to generate the superpixel for the topmost prediction. It means we are saying that African elephant was predicted with 82% of the probability. So that is our topmost prediction. So we are going to create the superpixel for this explanation, for this prediction. So this was the area which was responsible for predicting this image as the African elephant in the given image. So in the next step, we are taking the main reason which was responsible for predicting the African image. We are adding the remaining image back to this prediction. So here you will see that this was the area mainly responsible for prediction along with this remaining image. So this was all other part of image, but this is the area mainly responsible for highest or number one prediction. Next, we are going to visualize the pros and cons. So one big difference you need to look between these two images is that here you see that we are using positive only, they both are true, but here the rest of the image we are not showing, versus here we are showing the rest of the image. That's the reason we could see the rest of the image. So the code explanation was fairly easy. However, next we are showing the pros and cons, and then the only difference in the code is that here we are showing positive only equals true and positive only equals false. It means for the explanation of this result, we are showing all positive and negative related to this explanations. So let's run this code first. In the given image, this green area was the highly positive and the red area was the negative. It means this red area was not an active participant for predicting this image. So this image showing all the positives and the negatives used for explaining in this image, or just about explaining whatever the results were. And sometimes the positives or the negatives could be barely minimal, means they are 0.00 some percentage. So it's better to have only those pros and cons, positive or negatives, which are having some sort of significance. So the best option is to remove all those positives and negatives which have the weight less than 0.1%. So same code, the only big difference is that we are rendering the image and mask where the minimum weight is 0.1. And this way you could see that the majority of the clearance has happened, and all the very standard positive and the negative reasons related to these explanations are visible in front of you. So now we do see the high probability area related to our explanation, and looking into this image, this was the main, especially these two were the main areas which were responsible for this particular explanation. So after this significant pros and cons areas in the given image responsible for the explanations, we can actually generate the explanation heat map with all the weights we have related with the explanation. So let's run this first, and with the given image you can see that the minimum to the maximum. So where are the certain areas in this image which are responsible for the explanations here? So now you could see that this prediction being African elephant was mainly because of these areas, such as this was the mainly responsible for the African elephant. What if there was another area which has high probability as points like 1 or something like this? Then you could very easily figure it out that even the prediction was the elephant, however the reasons were wrong for making such prediction. Next, we can look into that what if the second prediction. We can look into the second prediction probability of being the Indian elephant is really very small, 0.06. However, we can give it a try for the second explanation. So the only big difference in our code is that rather than using the top labels, we are going to use the first label, 0 and first. So that will be our first. And as you could see, that being the second prediction as Indian elephant, these are the areas where mainly responsible. Now we are seeing those areas with the original image. Next, we are rendering the pros and cons and given image this. These are the pros area where this image was considered as the Indian elephant, and these are the negative areas. Next, we can remove any probability which is lower than 0.1, and because of that almost whole image, all those subpixels or subpixel regions are removed from this prediction. So that gives you the significance of this prediction. And if you try to generate the heat map, you are not going to see any of the values which is close to 0.1 or 1.01 and 1.0 on both sides for positive and negative. So this explanation should help you understand how a particular model which was created only to explain the results and how the explanations were explained to you for a particular prediction was made. And just once again, this explanation was part of the Lime explanation tutorial, so I have used as it is. However, I have another explanation to go a little more deeper to explain the results even at more granularity. So let's come back to this explanation, and this explanation has been taken from this GitHub repo. So I am using the explanation made by this GitHub repo, and in this Jupyter Notebook tutorial, we are going to learn two main things. First, we will prove the model agnostic part. It means we are going to use two separate models in our explanations. Second, we are going to use a custom code which is not specific to Lime, but it is made based on Lime research paper, and that is what is explainable in this code here in this lime.py. So explanations were understood through the Lime research papers, and this whole code was made. So the explanations are quite different in this Jupyter notebook. So I will give the credit to the writers who have created this explanation. I'm just using their code and their work to explain the Lime results. We are importing the Keras and NumPy, TensorFlow and other libraries so that our work would be easier. If you do not have Scikit image installed, make sure it is installed. It is already there. So this is the method which helps us to download the EffecientNet model. The EffecientNet model has the various versions where you could use a different image size. Depending on which image size you are going to use, a particular model will be downloaded. Basically, the model weights will be downloaded, which you could use to predict your image with whatever class that image belongs to. So here we are, depending on whatever type of model we want, that image size will be set for that model, and based on that image size, the tf.image.resize function will call to convert that image depending on whatever size we want. So this pre-process image method is going to be also available to set up your input image for whatever model type you have downloaded. So let me make sure this method is called, and this helps us to download the image in the current working directory. Here we are importing the V0 model, which means that our input image size must be set for 224, which will be downloaded for the EffecientNet. So right now we have our model, and the pre-process image method is available for us to call wherever applicable. We are importing the NumPy, and this elephant.jpg image, which is already available here, is going to be loaded, and we are calling this pre-process image, passing the image. So it means that our IMG is actually the 224 by 224 size. Next, we are using this model, which is the EffecientNet model here, and passing our image. It's the predictions coming out from this models are stored in this predict object. Let's make call. And now we are decoding the prediction by passing our predictions. And the very first prediction for us is the African elephant with a probability of 39%. Next, we are going to use this line explanation, which I have already told is defined here. And using the line explanation, we are going to perform the predictions similar to the Lime original explanations. So this Lime explanation code, which is Lime explanation, I have already loaded here, Lime explanations.py. So this code helps us to read the Lime explanation.py as import the Lime class, which is explained here. So Lime class. And we are passing our image, source image, and the EffecientNet model to generate the prediction. So this is our Lime object, which has the predictions. So first we are going to plot the original image, then we are going to plot the superpixel, then we are going to plot the perturbed image as part of Lime explanation, and finally we are going to plot the explainable image by passing the explainable model type using a decision tree regression. And in this example, we are rendering 4 images. This is the original image. Then we are creating the superpixel boundaries by defining the edges in the given image as best as we can. And here is the output image. Then after, we are generating the perturbed image, and finally the Lime explanations. So I will be explaining these results again at the bottom, but our next step is to use a different model. So initially we have used the EffecientNet model. Now we are going to use the ResNet model. ResNet 50 to be very specific. Next, we are downloading the ResNet 50 model locally. Now that model is available for us so that we can use that for prediction. We are loading the same elephant image, and finally using the ResNet model to generate the predictions. And these predictions are going to be stored in this ResNet 50 preds object. Now we are decoding the predictions, and the top 3. First one is the African elephant being the 78% probability, which is far better than the EffecientNet, which is 39%, and Indian elephant 12%, and the Tusker is 0.9%. So based on this model, now we need to generate the Lime explanations. At this point, I'm using the same method which I have used earlier so that we could use this image and pass in our Lime explanation. Now we are using the image which we have just read again because of the coding, but our model is the ResNet 50 model, and here the seed is still the same as before. So this is the new line object which is based on ResNet 50 model, and now we are rendering the results. Model explanations are model agnostics. You just need to pass the model and the given image or the given source data which you want to generate the local predictions. And as you could see that we have used the ResNet model, and even using that model we were able to generate the predictions. So now we can learn what is happening here. Very first step, we are creating the superpixel areas or superpixel boundaries. Next, we are creating the perturbed image by randomly filling some of the superpixel with the solid black color. So that's what you are seeing here in the second step. And for each perturbed image, because there are so many areas such as here, what we are doing is that we are creating the weights based on the difference between the perturbed image and the original image. So the smaller the distance, the larger the weight. It means they have the higher proximity. That is what happening here. And then finally, we are fitting a simple interpretable model, and in this case is a decision tree regressor. And here we are using the perturbed images, these areas, and the created weights based on the distance between the smaller, the close proximity to the original prediction. And in the fourth image, we are adding the image where we believe this prediction should be plotted. So it means this is the area which should be plotted for the superpixel with the highest importance in the model. Means the regressors which we have used, they have the highest coefficient value. So that's how this elephant image, or these are the areas within this image, has been used as the explanation to be the given explanation. So for example, if the results are shown as the African elephant, it means these are the given areas. They have been used to predict this image. If in this image, if this area has been used, or this area has been used, or this area has been used, even if your explanations were considered as the African elephant, you could not trust the results, because you as a human explainer, you could understand that yes, if this is the area has been used to explain that this is the African elephant, your results are good. Otherwise, the results are not good. So this is how a human chain can be added to explain the results and make them more trustworthy. And here are the functions just being used step by step, just to make sure that you get an idea. So here is the superpixel boundary, and then we are generating the perturbed image. So what is the perturbed image? It's basically is an image enhancement operator. That's why we call that image perturbation. So perturbation is two-step process. In the first step, we take the image and we try to look into the background and the foreground, and then apply the background slowness. That helps us to get the foreground image available, and then we improve that foreground image using an image enhancement operator. So that's what generates the perturbed image, and that's where it is. And then what we have done is that we have added a solid black color on that perturbed image to show that area more effectively. That's all we have really done here. And finally, we are plotting the explanation of the image by using a decision tree regressor, and that's how you are going to get the results specific to these particular model and the image explanation. And this is the step which was taking the longer time to complete, because here we are building a model and then showing the specific area of the image which were used to generate the prediction. And that explanation, the plot explainable image, has been used here. As you could see, and here is the whole area where we are performing the model.fit. It means a new model has been created in order to generate the prediction. So this explanation is similar to line, is not exactly the line, but it's based on the document or based on the research paper has been proposed through the line explainability. So in this tutorial, you have used two separate methods based on line to generate the explanations for our three different model: EffecientNet model, the Inception model, as well as the ResNet model. So now, before we go, let's move these two explanations, Jupyter notebooks, to this DeepWorks MLI XAI folder, so DeepWorks repo. So this notebook is going to be stored there in this repo, and similar to this, and this notebook is also going to be stored there. So now both these two Jupyter notebooks are available at this DeepWorks GitHub repo in this MLI XAI folder. So that's all I have for you in this tutorial. In this tutorial, we have covered two different line-based explanations. First, we have used the original line-based explanation with the Inception version 3 model. The second example we had with a custom line-based explanation, how the superpixel image is created and then perturbed image is drawn based on superpixel image, and finally the specific areas within the image were responsible for a certain predictions. So both examples were helpful for you to learn how you could use line to trust your model. Once again, I do appreciate your time. If you like the content, please do share it and subscribe it. I hope to see you in my next video. Until then, thank you so much for your time.